Alright, today let's have a look at topic 6, right triangles. So first, let's go over the concept of right triangle. A right triangle is a triangle that has right angle among its angles. The side opposite the right angle is called hypotenuse, and the other two sides are called legs. So in this figure to the right, AB is the hypotenuse, well, AC and BC are both legs. As you'll see through this course, many problems are solved by building right triangles and using the principle we'll learn in this chapter. So particularly one of the most famous math theorem of all is Pythagorean theorem. So first, let's have a look at the Pythagorean theorem, which states that right triangle ABC has hypotenuse AB equals C and legs AC equals B and BC equals A. So first of all, can you prove the Pythagorean theorem using similar triangles formed by altitude CD to prove that A squared plus B squared is actually equal to C squared? So I'll give you 1 minute to consider this problem, and then we'll have a look at the solution together, okay? Alright, have we finished? Okay, let's have a look at the solution together. So here we can know that triangle ADC is similar to triangle ACB, right? Therefore, we have B over E equals C over B. And then we have B squared equals E times C. And similarly, we can have triangle BDC is similar to triangle BCA, and therefore we have A over D equals C over A, right? So we have A squared equals C times D. So adding these expressions for A squared and B squared gives us left side is A squared plus B squared, and the right side is EC plus CD, which is C times E plus D. Well, E plus D is actually C, right? So that gives us a C squared. Therefore, we have proved A squared plus B squared equals C squared. This is one of the many methods we can use to prove Pythagorean theorem. Are you clear? Alright, so in a summary, in any right triangle, sum of the squares of the legs equals the square of the hypotenuse. For example, in the figure to the right, we always have A squared plus B squared equals C squared. This is famous Pythagorean theorem. Okay, now let's have a look at some exercises. So for each of the figures here, can you find the missing sides in the triangles below? Again, I'll give you 1 minute to think about this question, and we'll have a look at the solution together. Alright, have we finished? Okay, let's have a look at the solution together. So we can use Pythagorean theorem to help us to find the other side of each of the right triangles. So for the first triangle here, AB squared plus BC squared equals AC squared. So we can directly find BC squared is AC squared minus AB squared, right? So BC squared is 64 and we know BC is 8 here. For the second triangle, from triangle DF, we have D squared plus EF squared equals DF squared. So we have EF equals 8. And then consider the other right triangle there. We have EX squared equals FX squared minus EF squared. So EX here equals 15, right? And then consider right triangle GHI. HI squared plus GI squared equals GH squared. Therefore, we have HI equals square root of 147, and this gives us 7 times square root 3. For the last triangle, right triangle LKJ, we have KL squared equals LJ squared plus JK squared. So that equals 73. So KL equals square root of 73. It's a very straightforward question, right? So if you don't have any questions, let's consider another quiz. Isosceles triangle MON has MN equals NO equals 7 and MO equals 10. Can you find the area of the triangle MON? So note that this notation means the area of triangle MON. Again, I'll give you 1 minute to think about this question, and then we'll have a look at the solution together. Alright, let's have a look at the solution together. So first of all, we can draw altitude nx, which is perpendicular to MO at point x. So altitude nx cuts MO in half, so we have mx equals xo, which equals 5. The Pythagorean theorem applies to triangle MNX, which gives us mx squared plus nx squared equals mn squared, right? Therefore, we have 25 plus nx squared equals 49. And therefore, we have nx equals 2 square root 6. So the area of the triangle MON equals half of the base times the corresponding altitude, which gives us 10 square root 6. Very good. Alright, then consider another quiz. Suppose we have triangle ABC such that BC equals A, AC equals B, and AB equals C. And we have A squared plus B squared equals C squared. The question is that, is triangle ABC necessarily a right triangle? Which means is the reverse statement of the Pythagorean theorem is also true. Well, actually, we can consider this problem like this. If we have a squared plus b squared equals c squared. We do know that there is some triangle with side lengths ABC that is a right triangle. Because we have just proved that, right? Specifically, consider triangle DEF with angle F equals 90 degrees and EF equals A and DF equals B. Then Pythagoras theorem tells us that we have DE squared equals EF squared plus DF squared, which equals A squared plus B squared. Since we know that A squared plus B squared equals C squared, then we have DE must equal C, right? Therefore, triangle DEF is a right triangle with side lengths A, B, and C. Since triangle ABC has the same side lengths as triangle DEF, we have triangle ABC is congruent to triangle DEF by SSS, right? Therefore, triangle ABC must also be a right triangle. Can you see the logic here? So, put this in a summary. We have, if the sides of a triangle satisfy the Pythagoras theorem, then you know that triangle must also be a right triangle. Anytime you see triangle sides that satisfy the Pythagoras theorem, you should mark the angle opposite the longest side as a right angle. Can you follow me? Okay, now let's consider some other exercises. So here's the side lengths are marked in the diagram. Can you find the length of CD? Okay, when you finish, you can give me your answer in chat box. Alright, let's have a look at the solution. Since we have AB squared, so we know the lengths of AB, AC, and BC, right? We also see AB squared equal plus BC squared equals AC squared, right? Then we know that triangle ABC is actually a right triangle, and angle ABC must be 90 degrees. Therefore, triangle CBD is also a right triangle with hypotenuse CD. We can use Pythagoras theorem in right triangle BCD as well. So we have CD squared equals BC squared plus BD squared, which gives us 16 plus 81 equals 97. Of course, we know CD equals square root of 97, right? Okay, so now we have learned Pythagoras theorem, and next let's have a look at two special right triangles. So here, triangle XYZ is the isosceles triangle as shown with angle Y equals 90 degrees, given that XC equals 6. Can you find angle X and length of XY? Alright, let's have a look at solution together. Since the triangle is isosceles, the angles opposite the equal sides are equal, right? Therefore, we have angle x equals angle z. And since y is a right triangle, we have angle x equals angle z equals 45 degrees. To find xy, we use Pythagoras theorem. Xy squared plus yz squared equals xz squared. Since yz equals xy, and xz equals 6, so we can easily solve either xy and yz. So we have 2xy squared equals 36. Therefore, we have xy equals yz equals square root of 18. Of course, you need to simplify this to 3 square root 2, right? So this problem suggests that we might be able to find a general relationship among the sides in an isosceles right triangle. So to put this in a summary, in any isosceles right triangles, the legs are equal and the hypotenuse is square root 2 times the leg. Because the angles of an isosceles right triangle are always 45, 45, and 90 degrees, an isosceles right triangle is sometimes called 45, 45, 90 triangle. If we know the length of any side of such a triangle, we can quickly find the others using the side relationships shown in the figure at right. So, for example, if you have a 45, 45, 90 triangle, then if the two legs are x and x, then the hypotenuse is x times square root 2, right? Okay, for example, let's see another example here. How are the sides of a triangle? Oh, sorry. This is another special right triangle, which is called 30, 60, and 90 triangle. So, similar to what we have discussed previously, can you find the relationship of the sides of a triangle that have angle measures 30, 60, and 90? For example, if I let yz equals s, what is the length of xy and yz? Well, actually, in the right triangle with acute angles of 30 and 60, the sides are in a ratio 1 to square root 3 to 2, as shown to the right. So I'll leave this proof to you as a homework, okay? Try to see if you can prove this. So such a triangle is often referred as a 30, 60, and 90 triangle. So if one side, for example, yz equals s, the other two sides are just s times square root 3 and then s times 2. The hypotenuse is twice of the shortest leg of that right triangle. Any questions? Okay, if not, let's have a look at a quick quiz here. Can you find all the missing sides in the diagram? Which means AC, BC, BD, CD, EC, EF, and CF. Can you find all the sides here? Alright, so here let's have a look at the solution together. You can compare yours with mine. Because, first of all, because triangle ABC is 30, 60, 90 triangle, we have AB, and AB is opposite the 30-degree angle. We have AC equals AB times square root 3, right? Which equals 6 square root 3, that's AC. And BC equals twice of AB, which is 12, right? And then we can consider right triangle BCD. Right triangle BCD is a 45, 45, 90 triangle. We have BD equals BC, which is 12 as well. And CD equals 12 times square root 2. Then consider right triangle DCE, which is a 30, 60, 90 triangle, and CD is the longest leg. So we have CD equals DE times square root 3. Since CD equals 12 times square root 2, we have DE equals CD over square root 3, which gives us 4 square root 6. And then EC is twice of DE, which is 8 square root 6. Last, consider isosceles right triangle ECF, which is 45, 45, 90 triangle with hypotenuse EC equals 8 square root 6. Then we know the legs each have length EC over square root 2, which is 8 square root 3, right? Any questions?
No.
Okay, then another concept you need to know is Pythagorean triples. Pythagorean triple is actually a set of 3 integers that satisfy Pythagorean theorem. For example, 3, 4, 5 is a Pythagorean triple because we know 3 squared plus 4 squared equals 5 squared, right? On the other hand, we know 1, 2, 3 is not a Pythagorean triple since there's no way to add 2 of these 3 numbers to get the third. So very straightforward concept, right? Okay, let's consider a problem here. Question A, find the missing side lengths in each right triangle shown below. And based on that, consider the second question. Given that ABC is a Pythagorean triple, is 2A, 2B, 2C also a Pythagorean triple? How about NA, NB, NC, where n is a positive integer? Okay, let's do this together. So we can easily see that AC must be 5 here, right? And in the second right triangle, you can use a calculator to find EF is actually 8, right? For the third triangle, we have GH equals 12. The last triangle, we have XZ is 5, 5, 5, right? Can you see the patterns here? Well, this tells us that if ABC is a Pythagorean triple, actually if you multiply each of the 3 numbers using a positive integer n, then NA, NB, NC are actually also Pythagorean triple, right? Because we can prove this. So first of all, because we know a squared plus b squared equals c squared, for example, then we know that NA squared plus NB squared can be expressed as n squared a squared plus n squared b squared, and this gives us n squared a squared plus b squared, which equals n squared times c squared. So if you consider this is a number, this is another number, this is a third number, we have NA squared plus NB squared equals NC squared. Therefore, based on a squared plus b squared equals c squared, you can actually prove that NA squared plus NB squared equals NC squared. So NA, NB, NC is also a set of Pythagorean triple, right? Also note that n does not have to be integers actually to produce side lengths of a right triangle. For example, since triangle with side lengths 3, 4, 5 is a right triangle, then we know that 3 times 1 over 7, 4 times 1 over 7, 5 times 1 over 7 is also a Pythagorean triple. So actually n does not have to be positive integer, right? Okay, so in a summary, should be aware of this concept here. If ABC are sides of a right triangle, in other words, if ABC is a Pythagorean triple, then so are n, a, n, b, and c for any positive number n. For example, we know 3, 4, 5 are Pythagorean triple, right? Then all of these numbers are also Pythagorean triples, and all of these sets are also Pythagorean triples. Very clear? Okay, if no questions, let's consider another problem. First question, can you find the last side in each right triangle? And second, can you find any pattern? If you can find that, can you prove the pattern always works? So I'll give you 3 minutes here to consider this problem, and then we'll have a look at solution together, okay? Okay, let's have a look at the solution together. So first of all, let's find the other leg of each right triangles here. First one, the hypotenuse is 5. Second one of the legs is 8. Third, hypotenuse 17. Fourth, we know this leg is 10. And the last one, we know that leg is 35, right? So if we put this in a table, well, if we call the first column is the smallest even leg, the second column is the other leg, the third column is hypotenuse, then consider first right triangle 3, 4, 5. The smallest even leg is 4, right? And we know the other leg is 3. So actually 3 is, okay, let's just put this number here. And we know the hypotenuse is 5. And in the second triangle, we know the smallest even leg is 6, the other leg is 8, and hypotenuse is 10. And in the third right triangle, we have smallest even leg is 8, the other leg is 15, and hypotenuse is 17. Then in the fourth right triangle, the smallest even leg is 10, the other leg is 24, and hypotenuse 26. In the last right triangle, smallest even leg is 12, the other leg is 35, and hypotenuse is 37. So can you identify some patterns here? Well, actually, if we take the smallest even leg, halve it, and then square the result, for example, if you halve the first leg here, you will get 2, right? Then 3 is actually, okay, and then we take the square, 2 squared is 4, right? Then the other leg is actually this number here minus 1. And hypotenuse is actually this number plus 1, right? And do the same thing for the second triangle. 3 over 2 is 6 over 2 is 3. 3 squared is 9. So we use this number here. The other leg is just 9 minus 1. Hypotenuse is 9 plus 1, right? And you see the pattern here. For the third right triangle, 8 over 2 is 4. 4 squared is 16. And then we use this number here. The other leg is just 16 minus 1. Hypotenuse is 16 plus 1, right? So next one, 10 over 2 is 5. 5 squared is 25. Then we take this number here. 24 is actually 25 minus 1. 26 is 25 plus 1. And this pattern continues when smallest even leg is 12. 12 over 2 is 6. 6 squared is 36. And 35 is actually 36 minus 1. And 37 is 36 plus 1, right? So if the smallest even leg is, for example, 2n, of course we can still have it to get n. Then n squared equals n squared, of course. Then we know the other leg must follow the same pattern, which is n squared minus 1. The hypotenuse is n squared plus 1, right? So the problem is, can you prove this is always true for any number n where n is greater than 1? Which basically means one of the legs is 2n, the other leg is n squared plus 1, and hypotenuse n squared plus 1, right? Can you prove this is actually a Pythagorean triple? Of course, we can do this very easily, right? Because we can see 2n squared plus n squared minus 1 squared will give us 4n squared plus n to the power 4 minus 2n squared plus 1. And this gives us n to the power 4 plus 2n squared plus 1. And this can be abbreviated as n squared plus 1 then squared. As you can see here, you actually proved first number squared plus second number squared equals third number squared. Therefore, these three numbers is actually Pythagorean theorem, Pythagorean triple, right? Are clear? Okay. The next concept is congruence and similarity in the right triangle. So first of all, let's revisit congruence and similarity and apply this specifically to right triangle. For example, if you consider these two diagrams here, are the two triangles shown congruent? Why or why not? So actually the problem here is that SSA is not in general a valid congruence theorem, right? As we found in previous lesson. However, if we note that the angles that are equal are right angles, then things become different. We can use Pythagoras theorem to find AB and FG in both cases, right? In both cases, the length is square root of 100 minus 81, which is square root of 19. Therefore, by SSS or SAS, we have triangle ABC is congruent to triangle FGE. Well, by SSS or SAS. So this tells us one thing. In a pair of right triangles, if you can prove a pair of legs are equal and a pair of hypotenuse are equal, then we can actually prove these two right triangles are congruent, right? So in right triangles, this can be called HL congruence, which means hypotenuse leg congruence. So in a summary, if two right triangles have a pair of congruent leg and a pair of congruent hypotenuse, then we can conclude these two right triangles are congruent, which is called HL congruent for right triangles. Can you follow me? Okay, let's do an exercise here. So in the right diagram, can you prove that if the radius OC of circle O is perpendicular to the chord AB of circle O, then radius OC bisects chord AB? Can you prove this? So I'll give you 2 minutes to consider this problem, and then we'll have a look at the solution together, okay? Okay, have you finished? So we can actually have OA equals OV, right? Because they are both the radius of the circle O. Because we have OA equals OV and of course OX equals OX, which is obvious, then we have triangle OXA equals congruent to triangle OXB by HL congruence, right? Therefore, we have AX equals BX. So radius OC bisects chord AB, right? So in summary, if a radius of a circle bisects a chord of the circle, it's perpendicular to the chord. Conversely, if a radius of a circle is perpendicular to the chord, it bisects the chord. Are you clear? Okay, let's do another exercise. The center of a circle is 4 units away from a chord PQ of the circle. If PQ is 12, what is the radius of that circle? Okay, first of all, you have to construct the diagram by yourself. Okay, I'll give you 2 minutes to consider this problem. When you finish, you can give me an answer in the chat box. Alright, let's have a look at the solution together. First of all, we can construct the diagram like this. We have a circle, let's call circle O, and then we have a chord here, right? Chord PQ. And this is the center of that circle, we call it O, and well, we let M be the midpoint. Then if we connect MO, then we know MO must be perpendicular to PQ, according to the theorem here we have just proved, right? Note that M is the midpoint of PQ. Then connect MO, then MO is perpendicular to PQ, right? Because OM is part of the radius that is perpendicular to chord PQ, OM bisects chord PQ, so we have PM equals MQ, which equals 6, because PQ equals 12. And then finally we can apply the Pythagorean theorem to triangle OPM. Again, connect PO. Then in that right triangle we have OP just equals square root of PM square plus MO square. Well, MO is the distance between O and PQ, right? Then we know that gives us square root of 36 plus 16, which is square root of 52, alright. And simplify this to 2 square root of 13, right? Okay, if no questions, let's have a look at the next one. Another exercise. Are the two triangles in the diagram on the right similar? Why or why not? So here it looks like we can use SAS similarity, right? But SAS similarity requires the angle to be between the two sides that have the constant ratios. So we can't use SAS similarity like this. But we can recognize these two right triangles as 4, 3, 5 triangles, or we can use the Pythagorean theorem to find the other side. And we find that AB equals 9, QR equals 12. Therefore, we can have AB over RQ, which equals AC over PQ, which equals BC over PR. Therefore, we can prove triangle ABC is actually similar to triangle QRP by SSS similarity, right? So this tells us that in a pair of right triangle, by using HL, you can also prove that these two right triangles are similar. Okay, clear? Okay, if no questions, let's consider another important concept, which is called Heron's formula. Well, consider this introductory question here. In right triangle ABC, if we let AB equals C, AC equals B, and BC equals A, and let S equals a half of A plus B plus C. Well, in triangles, usually we'll use the letter S to denote half of the parameter of a right triangle, which is half of A plus B plus C. Okay, and then can you find the formula for the area of ABC in terms of S, A, B, and C? Okay, this problem seems a little complex. I'll give you 4 minutes to think about that, and we'll have a look at the solution together. Alright, let's try to do this together. So in order to find the area of triangle ABC, usually we'll use altitude, right? So first of all, we can draw the altitude AX, which is perpendicular to BC at X. Then let the height or altitude AX equals H. Then as long as we can solve H, then we can find the area of that triangle, right? So we let BX equals X. We let this length be X in order to help us to find the length H. Then we know xc must be a minus x, right? And we apply the Pythagorean theorem to triangle ABX and the triangle ACX. And we have x squared plus h squared equals c squared, and of course we also have a minus x squared plus h squared equals b squared, right? Again, we can subtract the second equation from the first to find x, which gives us x squared minus a minus x squared equals c squared minus b squared. Therefore, we have x squared minus a squared plus 2ax minus x squared equals c squared minus b squared. And therefore, we can actually solve x, which equals a squared plus c squared minus b squared over 2a, right? We know ABC, so x is solved. Finding h in terms of ABC seems a little complex. We can make the algebra somewhat nicer by solving x squared plus h squared equals c squared for h squared and factoring using the difference of squares. So first of all, we know h squared equals c squared minus x squared, and this gives us c minus x times c plus x, right? And then we can insert the value of x into that equation. First factor is just c minus, so note that x equals this expression here. So c minus x equals c minus a squared plus c squared minus b squared over 2a. And c plus x is c plus that expression over 2a. And then rewrite each of the factors using common denominator 2a. Then the first one gives us 2ac minus a squared minus c squared plus b squared over 2a. Second one gives us 2ac plus a squared plus c squared minus b squared over 2a. And the first one can be simplified to b minus a minus c times b plus a minus c. You see that? Over 2a. And the second factor can be simplified to a plus c minus b times a plus b plus c over 2a. And then simplify this. The product is b plus c minus a times a plus b minus c, then a plus c minus b, and a plus b plus c over 4a squared. So we can write h squared even more briefly with the substitution. Note that s equals a half of a plus b plus c, right? So that gives us 2s minus 2a times 2s minus 2c times 2s minus 2b. Then the last one is just 2s, right? Over 4a squared. And put the common factor 2 in front. We have 4s times a s minus A, S minus B, S minus C over 4A squared. And simplify this will give us oh, sorry, we don't have a 4A here, so let's correct this a little bit. So A squared. Okay, so that's the expression of H in terms of A, B, C, and S, right? And then we know the area of that triangle ABC can be expressed as half of BC times the altitude H, and this gives us A over 2 times the square root of H squared. H squared is this expression here, right? And this is simplified to square root of S times S minus A times S minus B times S minus C. So this means if you know the three sides A, B, C of a triangle, any triangle, then the area of that triangle can be found by using square root of S times S minus A, S minus B, S minus C. So in a summary, Heron's formula tells us that if the sides of a triangle are A, B, and C, and we let S equals half of the perimeter of that right triangle, which means S equals half of A plus B plus C, then the area of that triangle is given by this formula here. Square root of S times S minus A times S minus B times S minus C. Okay, clear? Okay, I'll give you 1 minute to write this down in your notebook if you haven't known this formula yet. Okay? Alright, have you done that? Okay, next let's have a look at quick quiz. Can you find the area of each triangle below using Heron's formula? Note that in each of the triangles here we know the three sides, right? So you can use Heron's formula to find the area of that each of the triangles very easily. For the first one, we know S equals half of the perimeter, which is 9, right? So the area of that triangle is square root of 9, that's S, times S minus first side times S minus second side times S minus third side. And this gives us 9 square root 3, right? So for the other triangle, you can use the same method to find the area of each of the triangles. So I'm not gonna cover all of them. You can use them as a homework, okay? Any questions? Any questions? All right, no questions. Let's have a look at the next topic, okay? All right. Now let's have a look at topic 7. In topic 7, we'll discuss the concept of special parts of a triangle. We'll divide this topic into two parts. In the first part, part A, we'll talk about bisectors, perpendicular bisectors of a triangle. In the second part, part B, we'll talk about the concepts of angle bisectors of a triangle, medians, altitudes, and have a look at some challenging problems if we have the time. Okay. First, let's have a look at the concept of bisectors. In general, any line segment from a vertex of a triangle to a point on the opposite side is called a cVN. The perpendicular bisector of a line segment is a line passing through the midpoint of the segment such that the line is perpendicular to the segment. For example, in this figure here, line K is a perpendicular bisector of AB because first of all, K is perpendicular to AB at point M, and we also have AM equals BM. Okay, clear? This is called perpendicular bisector. Next, the concept of angle bisector. Angle bisector of an angle is the ray that divides the angle into two equal angles. In this figure here, we have these two angles are equal, so ray M is the angle bisector of angle AOB. Okay, next let's have a look at some properties related to perpendicular bisectors or angle bisectors. First of all, line M is a perpendicular bisector of AB. Can you show that if C is on M, then we have CA equals CB? Okay, first we need to draw a diagram to show the situation here. So we have a segment AB. Line M is a perpendicular bisector of AB, which means line M is perpendicular to AB at some point M. We also have AM equals MB. Can you show that CA equals CB for point C is on M? For example, if C is here, any point on line M, can you show CA equals CB? Of course, we know if C is on top of M, CA is equal to CB because M in the midpoint, right? If C is any point other than M, can you also show CA equals CB? Well, actually, if we connect AC and BC, then we can easily prove that triangle AMC must be congruent to triangle BMC by using SAS congruence, right? Since AM equals BM, angle AMC equals BMC, which is 90 degrees, and CM equals CM, right? And therefore corresponding sides are also congruent. We can prove AC equals CB. You get it? Now consider if the reverse statement is also true, which means can you show that if AC equals BC, then C must be on the perpendicular bisector of AB? Okay, again, let's draw segment AB. And we have a point C somewhere here. Well, we know AC equals BC. Can you show that C must be on perpendicular bisector of AB? So first of all, if C is on the segment AB, we know C must be the midpoint. In that case, C must be on the perpendicular bisector of AB, right? If C is not on segment AB, can you still show this is true? Well, to show that C is on the perpendicular bisector of line AB, we can connect C to the midpoint of AB. So let's find midpoint of AB, then connect C and M, which we'll call midpoint M here. Then we can show CM must be perpendicular to AB in order to show C is on perpendicular bisector of AB, right? So in that case, AM equals BM. We also have CA equals CB and CM equals CM. Therefore, we have triangle CAM must be congruent to triangle CBM by SSS congruence. Therefore, we can prove angle CMA equals angle CMB, which is 90 degrees. Therefore, CM must be perpendicular to AB, and we also know M is the midpoint, so C must be on the perpendicular bisector of AB, right? Did you get it? So this tells us a very important property. The perpendicular bisector of a segment is a straight line consisting of all points that are equidistant from the endpoints of that segment. Right, clear? Okay, next let's consider the property of angle bisectors. First of all, can we show that any point on the angle bisector of angle XYZ is equidistant from YX and YZ? So first of all, let's draw an angle XYZ. We start by drawing the lengths we need to show equal. These are the perpendicular segments CP So suppose this is angle bisector, okay? And let's find a point C. Then we draw CP perpendicular to XY, CQ perpendicular to YZ at Q. So we can prove CP equals CQ, right? Of course, this is obvious because we can easily prove triangle CPY is congruent to triangle CQY by AAS congruence, right? Therefore, corresponding sides are also congruent, so CP equals CQ. Therefore, any point on the angle bisector of an angle is equidistant from the sides of an angle. Also, as with the perpendicular bisector, we can run this backwards, deducting that any point that is equidistant from the sides of the angle must be on the angle bisector. So consider this question here to see if you can show C must be on the angle bisector of triangle XYZ. So I'm not gonna cover this problem for you. You can use this as a homework, okay? But actually, we can prove both direction. And this tells us another important property. The angle bisector of an angle consists of all points that are equidistant from the sides of that angle. Any questions? Okay, if not,
No.
let's consider others. Perpendicular bisectors of a triangle. And first, let's have a look at its properties. Can you show that the three perpendicular bisectors of the sides of triangle are concurrent, meaning they meet at a single point? Show that there is a circle centered at this point that passes through all three vertices of the triangle. Again, we can start by thinking about just two of the perpendicular bisectors. So suppose we have triangle ABC here. Then the perpendicular bisector of AC, let's call it line L. Perpendicular bisector of AB, let's call it line K. We wish to show that O, which is the intersection point here, is on the perpendicular bisector of BC. Since O is on perpendicular bisector of AB, it's equidistant from A and B, right? We can connect OB, OC, OA. We know that OA must equal OB because it's on perpendicular bisector of segment AB. Similarly, since O is on the perpendicular bisector of AC, we also have OA equals OC. So OA equals OB equals OC. Since OB equals OC, we know that O must be on perpendicular bisector of BC. This is the property of perpendicular bisector we have just learned previously tells us, right? So the perpendicular bisectors of the sides of a triangle are concurrent. Also, seeing that OA equals OB equals OC, we note that if you draw a circle with center O and radius OA, the circle will pass through B and C as well, right? Because A, B, or C are equidistant to point O. And the point O and the circle described in this problem are so helpful in geometry problems that they have their own names. So let's put this in a summary. The perpendicular bisectors of the sides of a triangle are concurrent at a point called circumcenter. The circle centered at circumcenter that passes through the vertices of the original triangle is called the circumcircle of the triangle because it's circumscribed about the triangle, meaning it passes through all the vertices of the triangle. Finally, the radius of the circle is called the circumradius. The circumcenter is usually labeled with letter O, and circumradius is usually labeled as letter R. Are you clear? Okay, if no questions, let's consider another question. What is the circumcenter of a right triangle? What is the circumradius of a right triangle? So if we consider a right triangle here, let's call it XYZ. If we draw a few right triangles and their perpendicular bisectors, we will begin to suspect that the midpoint of the hypotenuse is the circumcenter, right? Probably somewhere here. So we can actually prove this. We start our proof by drawing the perpendicular bisector of one of the legs. For example, you can draw a perpendicular bisector of XY. Let's call it M, and it intersects with the hypotenuse at a point L. Since M and YZ are both perpendicular to XY, we have M is perpendicular to YZ, right? Therefore, we can easily have triangle XKL is similar to triangle XYZ. So we have XL over XZ equals XK over XY. Since XA over XY equals 1 over 2, we have XL over XZ equals 1 over 2. Then we can prove L is actually the midpoint of XZ, right? Clearly, L is also a perpendicular bisector of XZ since L is the midpoint of that hypotenuse. So L must be where the perpendicular bisectors of triangle XYZ intersect. Therefore, L is a circumcenter of triangle XYZ. This is a circumcenter. The endpoints of hypotenuse are vertices of a triangle, so by definition, they are on the circumcircle. Since the midpoint of the hypotenuse of a right triangle is a circumcenter, the hypotenuse is the diameter of that corresponding circumcircle, right? So to put this in a summary, we know that the circumcenter of a right triangle is the midpoint of the hypotenuse, and the circumradius equals 1/2 the length of the hypotenuse. Are you clear? And you should also note that there is an important property of the circles. Just as 2 points determine a line, we have now shown that 3 non-collinear points determine a circle. This means that given any 3 non-collinear points, there is exactly one circle that passes through all 3. Which means 3 non-collinear points can determine a unique circle. Okay, let's then consider exercise. Can you find circumradius of a equilateral triangle with side length 6? So first of all, let's draw a equilateral triangle ABC. Can you find the circumradius of a equilateral triangle with side length 6? When you finish, please give me your answer in the chat box, okay? Alright, let's have a look at the solution together. So suppose this is a circumcenter of that triangle. Then we can connect this circumcenter to a vertex and draw a couple of perpendicular bisectors as shown here and here. Then we can find the circumradius, which is actually OC, right? Since we have CQ equals CP and OC equals OC, well, sorry, let's call this point P and this point Q. We know that triangle OCP must be congruent to triangle OCQ by HL congruence because both of the triangles are right triangles. Therefore, we have angle OCQ must equal angle OCP. So OC must bisect angle ACB. Hence OCP equals half of angle ACB, which is 30 degrees, right? So if you consider this right triangle here, this is actually a 30, 60, 90 triangle. And we know that this length CP equals 3. Then we have OC equals CP times 2 over square root 3, which gives us 2 square root 3, right? So the circumradius of that triangle is 2 square root 3.
Yeah.
Alright, then let's have a look at the second part of topic 7. Okay. First, the concept of angle bisectors. The properties of angle bisectors of a triangle. Okay, first of all, can you prove that the angle bisectors of a triangle are concurrent? Again, let's suppose we have a triangle ABC. And we start much as we did with the perpendicular bisectors. We can consider the intersection of two of our angle bisectors, point I in the diagram. This is the one angle bisector. This is another angle bisector. This is a point of intersection. Let's call it I. Its equidistance from AC and AB. Since it's on the angle bisector of triangle ABC, its equidistance from AB and BC as well, right? Therefore, I is actually equidistant from all three sides of triangle ABC. Specifically, since I is equidistant from AC and BC, I is also on the angle bisector of angle ACB, right? Therefore, we have proved the angle bisectors of a triangle are concurrent. We found a special circle also, right? Because if you draw a perpendicular line here, draw a perpendicular line here, draw a perpendicular line here, actually this segment equals this segment equals this segment. So if you draw a circle here, we have found a special circle which is centered at the intersection of the perpendicular bisectors. And then we can try to see if the intersection of the angle bisectors is the center of a special circle too. Let's consider another problem. So here, I'm not cover this problem. You can read it and copy that problem on your notebook. Try to prove this on your own as a homework, okay? The angle bisectors of triangle XYZ meet at I, and perpendicular segments from I to the sides of a triangle are shown as below. Well, first problem, why is IR equals IQ equals IP? And suppose we draw a circle with center I and radius IP. Does the circle hit YZ at any point besides P? Also, can you show that circle from B is tangent to sides X, Y, and X, Z at point Q and R and Q respectively? So try to consider this problem on your own after this class, okay? Actually, these two questions gives us a very important property of angle bisectors of a triangle. So let's put this in the summary here. The angle bisectors of triangle are concurrent at a point called the incenter. Be careful, this is different, sometimes different than the concept of circumcenter. Okay, they are not necessarily the same point, but sometimes they are the same point. For example, in the six E triangle, they are actually the same point, right? Equilateral triangle have same incenter and circumcenter. And the incenter, this point, is equidistant from the sides of a triangle. This common distance from the incenter to the sides of a triangle is called inradius. Because the circle with center I and this radius is tangent to all three sides of a triangle. Actually, we can prove this in this question here. So this is why I asked you to see this question to see if you can prove that by yourself. This circle is unsurprisingly called the incircle because it's inscribed in the triangle, meaning it's tangent to all three sides of the triangle. The incenter is usually denoted I, and inradius is usually written as R. Okay, clear? And let's consider another question. Given that E is on segment AC such that BE is a bisector of angle ABC, can you prove AB over AE equals CB over CE? Again, first of all, let's draw a triangle to illustrate the concept here. We have a triangle ABC. E is on AC such that BE bisects AB's angle ABC. Can you prove AB over AE equals CB over CE? So this angle equals this angle. So I'll give you 1 minute to consider this problem, and then we'll have a look at the solution together. Okay, let's have a look at the solution together. So seeing ratios here, we can think of similar triangles, right? Similar triangles make us think of parallel lines. So we can draw a line through point C such that this line is parallel to segment AB. This is possible by using straight edge construction. So draw a line here and extend BE past E to hit this new line at some point X. This is also possible, right? So note that CX here is parallel to the line segment AB. So again, I'm not gonna write all the descriptions here. Make sure you write all the descriptions. Tell your reader how do you draw the auxiliary lines. So we pick this parallel line to draw because it let us use the angles that are formed by the angle bisector. Specifically, we have angle BXC equals angle ABX. which is angle here. BXC equals angle ABX because of parallel lines, right? And this also equals angle XBC. So triangle XCB is isosceles triangle. And therefore we have CB equals XC. Sorry, CB equals CX. This side equals this side. Our parallel lines give us similar triangles. Triangle ABE is similar to triangle CXE. The similarity gives us AB over AE equals CX over CE. Since CB equals CX, we have the desired ratio AB over AE equals CB over CE, right? Again, in a summary, this tells us another important property of the angle bisector of a triangle. So let's put this in the summary. The angle bisector theorem states that if E is on segment AC such that BE is the angle bisector of B in ABC, then we have the following conclusions. AB over AE equals CB over CE. We should think of this anytime we have a problem involving lengths and angle bisectors, right? Okay, now let's have a look at some exercises. First of all, can you find AC and XQ in the diagram where XZ equals, also note that XZ here equals 12, not QZ or XQ, okay? Again, when you finish, please give me your answer in the chat box. Alright, because of the time constraints, it's better to have a look at the questions together now. So from the angle bisector theorem, we can apply it to triangle ABC first. We have AB, sorry, use another color. Okay, first of all, we have AB over BD equals AC over CD, right? Because as you can see here, this angle equals that angle. Of course, we have AB over BD equals AC over CD. And this gives us 12 over 6 equals AC over 7. Therefore, AC equals 14, right? In the second question, finding XQ is a little more challenging. But we can let XQ equals X to facilitate our discussion. So in that case, QZ is 12 minus X. The angle bisector theorem tells us that XY over XQ equals ZY over ZQ. So we have 9 over X equals 8 over 12 minus X. Cross multiplication gives us an equation in which we can solve the value of X, right? Well, this gives us X equals 108 over 17. And therefore we can find X cubed equals 108 over 17. Any questions? Okay, then if no questions, let's consider another important property. that is related to the in radius and side length. Well, can you find the area of triangle XYZ in terms of its in radius and its side length? Well, for example, if we consider a triangle here, suppose this is its in circle, and this is the center of the in circle. We know that the three radius are perpendicular to the three sides like this, right? Let's call the theta perpendicular be P, Q, R respectively. Those radii of the in circle perpendicular to the sides makes us think of altitudes. So indeed, if we break triangle XYZ into three triangles with I as a vertex, these radii are altitudes, right? Adding the areas of these three triangles gives us the area of the entire triangle XYZ. So here, the entire area of triangle XYZ can be broken down into xi plus yzi plus xei. If you draw these auxiliary lines as well, and the area of xyi equals ir times xy over 2 and plus ip times yz over 2 plus iq plus times xz over 2, and this gives since ir equals ip equals iq, which is r, the in radius, and xy plus yz plus xz equals 2s, where s is a parameter of triangle XYZ, right? Sorry, is half parameter of XYZ. Then we have triangle XYZ equals r times xy over 2 plus r times yz over 2 plus r times xz over 2, and this can be simplified to r times xy plus yz plus zx over 2, which equals r times s, right? So this tells us we can use the radius and side lengths to find the area of any triangle XYZ. So in a summary, the area of a triangle equals its in radius times its semi-parameter. Area of triangle ABC equals RS, where R is the in radius and S is the semi-parameter. Are you clear? Okay, consider a quick example here. Okay, find the radius of circles that's tangent to all three sides of triangle ABC, given that the sides of ABC have lengths 7, 24, 25. Have you got an answer? So note that we have 7 square plus 24 square equals 25 square, right? This triangle is actually a right triangle with legs of 7, 24. So we can easily find the area of that triangle ABC equals 7 times 24 over 2, which equals 84. Since we can also find the semi-parameter, you can find the in radius as well. Semi-parameter equals 7 plus 24 plus 25 over 2, which equals 28. Then we have in radius equals the area of triangle ABC over S, which is 84 over 28, which equals 3, right? Right there. Okay, if you don't have any questions, let's consider the concept of medians. A median of a triangle is a segment from a vertex to the midpoint of the opposite side. In the figure below, AD, BE, and CF are all medians. The medians of a triangle are concurrent at a point called centroid of the triangle. The centroid of the triangle is usually labeled G. So here I'm not going to prove this property for you. Once you have learned the concept of analytic geometry, this can be easily proved by using analytic geometry. Okay, next let's have a look at some important properties of median and centroid. So first, can you prove that the medians of a triangle divide the triangle into 6 triangles with equal area? Okay, for example, let's consider this triangle here. We can easily see that the area of triangle BGD, which is here, equals the area of the triangle CGD, because these triangles have the same altitude from G to equal bases BD and CD, right? Similarly, the area of triangle AGE equals the area of triangle CGE for the same reason, right? And the area of triangle AFG equals the area of triangle GFB for the same reason. We assign variables to these areas as shown. For example, we let this area be Y, this area be X, and these two areas are Z. The little triangles aren't the only triangles that share the same altitude, since triangle ABD and triangle ACD have the same altitude from A to equal bases BD and DC. We also have the area of triangle ABD equals the area of triangle ACD, right? Therefore, we have x plus 2z equals x plus 2y. Therefore, we can prove y equals z. Similarly, we can use the area of triangle AFC equals the area of triangle BFC to show that x equals y. Therefore, we can actually show x equals y equals z, right? And therefore, all the 6 little triangles have the same area. Did you get it? So let's put this in the summary. The medians of a triangle divide the triangle into 6 triangles of equal area. So in this diagram here, suppose AD, BE, and CF are the medians, then we have the area of these triangles are equal. AFG, BFG, BDG, CDG, CEG, and AEG. Are you clear? Okay, then consider another property of the medians. Can you prove the centroid of any angle cuts each of the triangles median in a 2-to-1 ratio, with the longer portion being the segment from the centroid to the vertex? Again, let me draw you a triangle here. C, A, B. Then F is the midpoint, CF is the median, BF is also a median, AD is also a median since this is a centroid, which is denoted as letter G. Any ideas? Our work with areas gives us the solution right away, right? Since triangle AGB, if you consider triangle AGB, consisting of 2 of the little equal area triangle, and triangle GDB is only one of them. We have the area of triangle AGB equals the area of triangle 2 times the area of triangle GDB, right? From the previous question, we know this. And these 2 triangles share an altitude from B to base AG and GD, right? Therefore, we have AG over GD equals the area of AGB over the area of GDB, and this ratio is 2, right? Clearly, this works for any median. So if this length is x, we know this length must be 2x. Did you get it? So put this in a summary. This tells us that the following important property: the centroid of a triangle cuts its median into a 2-to-1 ratio. For example, for the triangle shown on the right, we have AG over GD equals BG over GE equals CG over GF, which equals 2-to-1. All right, so let's consider another quick quiz. Triangle PQR is an equilateral triangle with side length 12. Can you find the length of the in radius of triangle PQR? We have a triangle PQR here. A in circle of that triangle is here. Apparently, the in radius is the intersection of 2 angle bisectors. So let's call PL is angle bisector of RPQ, and RN is the angle bisector of angle PRQ. Since angle bisectors and equilateral triangle are also medians of triangle, L is midpoint, right, of RQ, and in center I is also the centroid. So this point here is also the centroid. So I divides median PL such that PI over IL equals 1 over 2. Therefore, we know IL equals PL over 3. Again, triangle PLR is a 30, 60, 90 triangle. So we have RL equals PR over 2, which is 6. And PL equals RL over square root 3, which is 6 square root 6, right? Finally, we have IL equals PL over 3, and this gives 2 square root 3, right? Okay, then next let's consider another property of related to medians. Can you prove that the 4 small triangles in the figure on the right are congruent and that each is similar to triangle ABC? Note that D, E, F are the midpoints of BC, AC, and AB respectively. So this is a pretty straightforward question, right? I'll give you 1 minute to think about this question. Okay, so triangle FAE and triangle BAC have an angle in common, but we don't know anything about the other triangles, other angles of that triangle. So we look to SAS similarity to prove similarity, right? Since AF over AB equals AE over AC, which is 1 over 2, we have triangle FAE is similar to triangle BAC by SAS similarity. Similarly, we can also show triangle FBD similar to triangle ABC, and triangle CEG is similar to triangle CAB, right? Since each of the small triangles above have same lengths that are 1 over 2 the size of triangle ABC, we have FE over BC equals DE over AB equals DF over AC equals 1 over 2, right? Therefore, we have triangle DEF is similar to triangle ABC by SSS similarity. Since all of 4 little triangles are similar to triangle ABC with same side ratio, the 4 little triangles must be congruent, right? So let's put this in a summary. Given that triangle DF is a medial triangle of triangle ABC as shown below, we have the following relationships. First, triangle DF is similar to triangle ABC. Triangle DF is congruent to triangle FBD, which is congruent to triangle AFE, which is congruent to triangle EDC. All the 4 little triangles are congruent. And second, EF over BC equals DE over AB equals DF over AC, which equals 1 over 2. Third, DF is parallel to AC, EF is parallel to BC, and DE is parallel to AB. Together, facts 2 and 3 are sometimes called midline theorem. Again, because of time constraints, I'm not going over all the exercise for you, so if you have the time, please use this as your homework, okay? And one last property regarding the special parts of a triangle is the altitude. Well, we can actually prove that all the lines containing the altitudes of a triangle are also concurrent. Again, I'm not going to cover all of these. Please consider how to prove this by yourself on your own after this class, okay? Well, actually, this is not difficult to prove. The altitudes of any triangle are also concurrent at a point, and we call this point the isocenter. We usually denote the isocenter with letter H. Again, I'll show you some exercise problems. You can use them as the homework, okay? So please take a snapshot of each of the exercise here. If you have any questions, you're very welcome to send me any message, okay? This is the first one. Second one, again, these are some challenging problems. Because of time constraints, we cannot cover all of the questions here. So please take a snapshot, and if you like, we can discuss them in our next lesson. First problem, second one. Third one. Fourth one. And last one. So the last 5 problems are challenging problems in this topic of geometry, special parts of a triangle. Okay, again, if you don't have any questions, I'll see you in next lesson.